I started my lecture with this diagram, where you have a continuous function of one variable. You sample it using an impulse train, apply the discrete Fourier transform, get f tilde, and from f tilde so you know now that this is going to be some box filter times f tilde, right? And you get one period from which you can reconstruct using the inverse Fourier transform, the original f of t. Okay, so this same setting works in the 2D situation also, for a two-dimensional function also. Okay, so in the two-dimensional case, we will talk about two variables, continuous variables t and z. So these will be our continuous variables. Okay, and ftz will be the continuous function, which after sampling. So in sampling now we will use the variables delta t in the t direction, delta z in the z direction. Okay, we will sample these to get f tilde xy. Okay, so this is the sampled function f tilde xy. To this, you can apply the discrete Fourier transform and get capital F. The frequency variables will be u and v now instead of just u. Okay. F tilde. Now from f tilde, you can get again f, okay, by choosing one period. Okay, and then this function and this function are related by Fourier transforms. Okay, so this is a FT pair, right? So the same setting as earlier. So now again, the results for one dimensional can be carried over to two dimensions with not much difference. Okay, again the same sampling theorem will hold here between the sampling intervals delta t, delta z, and the corresponding frequency domain intervals. So the frequency domain intervals, we will call them delta u, delta v, are as follows. So if you remember this, this is similar to what we have done for the one-dimensional case. Okay. If ftz is sampled to form the discrete function fxy, okay, function of discrete variables x and y, which will be an m cross n array with m samples taken in one direction, n samples in the other. Okay, with m samples taken in, let's say, the t direction, and n samples in the z direction. Then delta u will be 1 over m times delta t, and delta v will be 1 over n times delta z. Okay. Similar to what we had in the one-dimensional case. The point to note here is that these separations are proportional not only to delta, inversely proportional not only to delta t and delta z respectively, but also to m and n. Okay. So the separations between the samples in the frequency domain are inversely proportional to both the spacing between the spatial samples and the number of samples. Okay, so here we are, if you want to sort of see the picture, so we are taking this sampling in the t direction at intervals delta t, sampling in the z direction at intervals delta z. Okay, so these are m samples numbered from 0 to m minus 1, n samples in this direction numbered from 0 to n minus 1. Okay, so what we are saying is that when you look at the corresponding spacing here, okay, in the u and v directions, okay, so this is u direction, this is the v direction. Okay, then the spacing here, this is delta u, and this is the spacing delta v. So these are the relations between these two. I will complete the notes here, whatever I've just said, that it is important to note this inverse proportionality. Okay. Okay. So some properties that are important. Properties of the two-dimensional discrete Fourier transform and inverse discrete Fourier transform. So I'm going to list them, write or describe these as briefly as possible. You can read more details whenever the need arises. Okay, so I've tried to collect the most important ones. There are a lot of these properties. Okay, so let me just remind you, in two dimensions, the discrete Fourier transform has this formula: fxy e raised to minus 2 pi I. So now this is ux over m plus vx, vy over n, where your x and y vary from 0 to m minus 1 and 0 to n minus 1 respectively. Okay. And the inverse discrete Fourier transform has the form fxy equals 1 over mn. So I think one of the homework problems is to prove this 1 over m for the one-dimensional case. Okay. That same thing will carry over for two dimensions. Capital FUV e raised to 2 pi I ux over m plus vy over m. So just note that uv and xy are both varying over the same number of samples. Okay, so the number of samples in both is going to be the same. Okay, in the discrete case. Okay, so the properties. So let me start listing them one by one. So first, translation. So this I will not prove. It can be checked, and it's not difficult also. Mathematically quite straightforward to check that fxy, if you multiply fxy by e raised to 2 pi I u naught x over m plus v naught y over n. Okay, so you have this function fxy to begin with. Now you're multiplying it with this and looking at the Fourier transform of this. Okay, then this, the Fourier transform of this will be f u minus u naught v minus v naught. Okay, so if you multiply the original function with this, then the Fourier transform is shifted. Okay, so that is what this means. So multiplying f, i.e. multiplying f by this exponential shifts capital F. Okay, so that's one thing. Second, if I do the shifting here, okay, fx minus x0, y minus y0, and then apply the discrete Fourier transform, okay, then we get this e raised to 2 pi I x naught u by m plus y naught v by m by n. Okay, so now this here the shifting or the translation was being done here. Okay, so this is this means multiplying. If you multiply capital F, so this is a Fourier transform pair. Okay, so multiplying capital F by, see this, it is the same exponential function with a minus sign, by this exponential inverse, okay, shifts small f. Okay, so if there is a shift in the image, that corresponds to multiplying the Fourier transform with this exponential function. Okay. And on the other hand, if you want to shift the Fourier transform, then you multiply the original function by this exponential. Okay, so these are actually very important properties, and we will use them in the later properties and even in the construction of the spectrums. Okay. So I will mark these as star. Actually, I will just mark this one as, this is the more important. Okay. Another thing to note from this is that this translation, from this, okay, one thing to note from this is that you're doing translation on the image. Okay, so the translation on the image has no effect on this part or the magnitude of the Fourier transform. Okay, the only effect is you're multiplying this. Okay, the magnitude does not change. Okay. So translation also, translation has no effect on the magnitude of FUV, magnitude of FUV. Said another way, this is a complex number, so you can write this as mod FUV times e raised to something. Okay, so this e raised to and this e raised to will combine, but this mod FU does not change. That is what this means. Okay. Then the next property I want to talk about is rotation. So you can consider polar coordinates on both sides. X equal to r cos theta, y equals r sin theta for the xy variables. And for the uv variables, let's consider omega cos phi and v equals omega sin phi. Okay, so if we consider these polar coordinates, then the Fourier pair is given by f r theta plus theta naught. So what we are doing here is changing the angle, okay, doing rotation. The original image is being rotated by an angle theta naught. Okay. This is a pair with omega phi plus theta naught. So this is saying that, so we have this original pair f r theta, capital F omega phi, right? So if this is a Fourier transform pair, then this is also a Fourier transform pair, which means that if you rotate the original image by theta naught, then the Fourier transform or the spectrum also gets rotated by theta naught. Okay. So actually, let me show you some figures to explain what I'm saying here. Page 250 here. So here they have computed the spectrum of a rectangle. Okay. So this is the original image. Okay. And this is its spectrum. Okay. So you don't see anything here really, because the the thing to observe is happening at the corners up here. Okay. Up here you can see some white and some white pixels here. Okay. So that is actually the spectrum. Okay. In general, what is done is this interesting part, which is up here, is shifted to bring it to the center. Okay. So this is where the action is happening. So some shifting is done, translation in the original image, to bring that here. Okay, we'll talk about that in a moment. How to bring something that's at these corners to the center. Okay. So this image, after shifting, it has come here, and now it can be observed that most of the action is happening here. Okay. And these are not clearly visible. Okay. So what is done is these intensities are spread using the log function. Okay, to get this final image. Okay. So this is how the final image of the spectrum is obtained. So if you just apply Fourier transform, you will get this. With some shifting, you will get this. Okay, the origin shifted to the center. And then applying the log function will give you this spread out spectrum. Okay, so this is how the spectrum of the original image is obtained here. Okay, and what I'm describing to you just now is saying that translation. Yeah, so now this rectangle is translated from somewhere to here. Okay, but the spectrum has not changed. If you compare this spectrum with the earlier one, okay, the spectrum is the same. The position of the rectangle has changed. So that is what this is saying, that translation has no effect on the magnitude of the spectrum. Okay. Whereas rotation, if the angle is rotated by some angle, the spectrum rotates by the same angle. Okay. That is what this figure demonstrates. So rotation of capital F or small f by theta rotates the other one. So rotates small f respectively capital F by the same angle. Okay. That is what I have stated. The third thing I want to talk about is the period of this periodic function capital F. Okay. So this is what the centering thing I was talking about earlier. So F is centered at 0. At 0. So the samples are in, so if I want to draw the picture, okay, so this is U, V, okay, and F we cannot see when F is plotted, okay, but we can only see these variables, okay. Now these are sampled in the intervals minus m by 2, m by 2, okay, at least when we drew the original pictures, this is how it was happening, right? Minus n by 2, n by 2. What we would like though is these to be sampled not that way, but in 0 m minus 1, okay, and in 0 n minus 1 for some m and n. Okay, so instead of looking at this square like this, okay, we would like to look at this square or rectangle, okay, as it may be, if m is not equal to n. We would like to look at this. Okay, the reason is that, well, if you have something centered at the origin, okay, if you are looking at say this kind of function, then this is fine. But on the other hand, if you're looking at a function which is what happens quite often. So I shouldn't be saying this actually, because I might be wrong. Yeah, let me not say this at all. So what I want to say is that it is desirable to have this sampled in these intervals. Okay, 0m-1, 0n-1, even for calculation purposes. Okay, so so the point is that this is centered at origin. You would like to have it centered instead here. Okay, now this point is actually half of this and half of this. So to make sure that we end up with integers, what is done is the floor of m/2 and floor of n/2 is taken. Okay, and this is the point. So this function f, so that f00 will lie here now instead. Earlier f00 was here, lying at this origin. What we would like to do is move it so that it lies here. Okay, and this is where the star will play a role. What the property that we just saw here. Okay, so now you want to move from 0 to m/2 n/2. Okay, so then you have to multiply the original function by some exponential. Okay, so now our u0 and v0 are going to be m/2 and n/2 respectively. So if we do that substitution, we will get the exponential function that needs to be multiplied to fxy to affect that shift. Okay. So to shift, so f is centered at 0. So samples are in the interval. This is what this first figure is describing. Samples are in the interval minus m/2 m/2 cross minus n/2 n/2 to shift the center to floor m/2 floor n/2. Okay, that is the interval 0m-1 cross 0n-1. So if you want to shift the action here, okay, then the idea is to multiply fxy. So this is from the earlier property, multiply fxy with e raised to 2 pi I. You take u0 to be m/2 and v0 to be n/2. So u0 x by m plus v0 y by n, where u0 is m/2, v0 is n/2. So if you just do those substitutions, you get, so this equals e raised to 2 pi I x plus y. Okay, so this will be just the cosine function with these periods. So this is going to be minus 1 raised to x plus y. Okay. Depending on the values of x and y. So this function comes out to be this. So essentially what it means that fxy multiplied by minus 1 raised to x plus y is a Fourier transform pair with capital F u minus m/2 floor actually v minus n/2. So I will remove that floor with the understanding that we are always taking the floor function. Okay, so this will shift the data, will shift the data so that f00 is moved to the center of the rectangle of the rectangle 0m-1 cross 0n-1. Okay, like in this image here. Okay, So the action was happening at these corners. Okay. Now that has been moved to the center exactly by this process. Okay. The original function was multiplied by -1 raised to x plus y, so that the corners move to the center here. Okay. Earlier I refrained from saying why, but now we can sort of explain. Okay. Uh, so when I talk next about the Fourier spectrum, there is something to be said about symmetry. Okay, a lot of things about symmetry. There is a lot of symmetry behavior in different ways. Okay, but this is a topic too much detailed. Okay, so I don't want to go into this. So I'm going to skip this. We'll skip due to lack of time. But if you are ever in a situation where you want to design a filter, then you probably should go through this. So I'm going to skip this whole discussion of symmetry and move on to Fourier spectrum. This is also called as magnitude or frequency spectrum or frequency spectrum. Okay. So this is what is being plotted in this image here. Okay, the magnitude spectrum. Sorry, here. So we know that FUV is a complex number. We can write it as the real part plus its imaginary part, okay, which is mod FUV. In polar coordinates, you can write it like this, I phi UV. Okay. So if mod FUV is plotted against UV, that gives us the Fourier or magnitude or frequency spectrum. Okay. So plotting mod FUV gives the magnitude spectrum. I think I said this already last time. Somebody asked me how this is plotted. So this is plotted on 2D simply by taking UV and at the position UV, you plot mod FUV. Okay. So if this position is if this position is U0 V0, okay, then at this position, the value of mod F U0 V0 is plotted. Okay, is plotted at position U0 V0. Okay, this is some U0, some V0. So this is how the plotting is done. Then if you are plotting instead of mod FUV, if you plot phi UV, then that gives the phase angle or phase spectrum. Okay, so we haven't seen an example of this yet. I will show you in a few minutes. Both of these will be considered, will be arrays of size m cross n. Okay. Both are arrays because you have this size, these are m points here and n points here, arrays of size m cross n. Okay, both these satisfies just the following thing I will write, not proof. Mod FUV is same as mod F minus U minus V. So there is this symmetry in the plots. Okay, and phi UV is same as minus phi minus U minus V. Okay, so when the plot is made, so suppose this is m minus 1, n minus 1. Okay, and if the plot is in this region, Okay, and F00 is plotted here at m by 2, n by 2. Okay, then that gives the first property gives us a symmetry across this line, and the second property tells us that anything in the sort of this first quadrant here will appear here. Okay, and anything in the second quadrant will appear here. Okay, along with this minus sign, some kind of rotation, reflection rotation symmetry. And finally, the third point to note about these plots is that what is this F00? So by the formula for the discrete Fourier transform, this is fxy, right? 0 to m minus 1, 0 to n minus 1. You can think of this as mn times this sum divided by mn. What you have here is the average of the given image, right? The sum of the pixels. So this is mn times, let me write f bar. Okay, this is average of fxy. So this F00 term, okay, is nothing but is proportional to the average of fxy. Okay, so that is why what the F00 term is actually giving you is sort of the average intensity in the original image. Okay, it is proportional to this average intensity on the original image. Okay, and that is why you want to see it at the center here, which is why you do this shifting. Okay, so this is what I was trying to say earlier. Why should you do this kind of shifting of origin? Mainly for this reason, because F00 plays an important role in the intensity profiling. Okay, it is actually the overall the average intensity of the image. Okay? So that is why one goes through this whole process of shifting the F00 to this point. Okay, it's an important point and you want to see it, not let it be at the corners. Okay, then the next point is the 2D convolution, discrete convolution theorem. Okay, so I'm just going to state this. We have already seen this in the one-dimensional case. So this is Fmn h x minus m y minus n going one way. So this is the formula for the convolution. Okay, so when we talk about the Fourier transform pairs, f star h xy and f dot h, this is multiplication uv, this is a Fourier transform pair. Okay, so this is your formula, and these are the two Fourier transform pairs for going from spatial to frequency domain and vice versa. Okay. And multiplication in the spatial domain corresponds to convolution in the Fourier domain with this coefficient. Okay, so these I will call star and double star. Okay, or maybe star, double star. So this formula actually, the first one here, okay, this is the foundation for all linear filtering in the frequency domain. Okay, so this formula is the foundation for linear filtering in the frequency domain, because this tells us how you go back and forth in the case of images. Then when one is actually doing the calculation, one needs to consider this wraparound error, okay, and padding. So coming to padding, so last time Shailendra asked me if there is only one way to do padding. So turns out there are more than one ways. Okay, so padding can be done in various ways. One is the zero with zeros. Okay, the other is what is called as mirror padding. Okay? And there is one more which is called as you just extend the image, so that is replicate padding. Replicate padding. So you can read more about this on page number 171 and 172 pages of the text. But essentially what in zero padding, what you do is you take the image and just pad with zeros, that you know. In mirror padding, you consider these to be mirrors, and the whatever this padding that you want to do, it's a mirror image of these pixels here. Okay, considering this to be the reflection axis. Similarly for all four sides, that's mirror padding. And replicate padding means these same pixels are just replicated in that same order here. Okay. So these are the three, at least so far, these three kinds of padding. Okay, and they have their own advantages and disadvantages. I won't go deeper into that. You can look at the reference. So the wraparound error happens because, so one wants to consider the following. Yeah, so ultimately what it is that we are interested in the results of convolution in the spatial domain, right? Where that is where we are going to essentially analyze the images. Now the convolution theorem tells us that there are two ways of computing spatial convolutions, right? We can do it directly in the spatial domain as we saw earlier, or we can compute the Fourier transform of each function, then multiply those functions and compute the inverse Fourier transform, right? So this is the second way of doing it. Now, because we deal with discrete quantities in this Fourier domain, the computation of the Fourier transforms is carried out using this discrete Fourier transform. Now, in discrete Fourier transform, the formula that we wrote above, okay, you can see that where did we write it? Periodicity. Okay. So the periodicity gives rise to, so there is one periodicity coming here and one coming here. Okay, so the question is, doing all this process, okay, when does the direct spatial approach give you the same result as this Fourier domain approach? Okay, so with all these factors coming into play, the question that one needs to ask is, under what conditions is the spatial domain approach, or will the spatial domain, direct convolution in the spatial domain, and the Fourier transform method give the same result? Okay, so that is a natural question to ask. So there are a number of things to be said about this, but the direct or the short answer is that you will get the same result if you apply padding to the original image. Okay? So you apply padding to both the function as well as the kernel, okay, both f and h, so that they have the same length p. Okay, so this length, so I can quickly describe to you what happens through this image. So this is what convolution does, right? So you have your original function f here, okay, and so this is in the, this left hand side is happening in the spatial domain, right hand side is happening in the Fourier domain, okay. In the spatial domain you have this, in the Fourier domain it's going to actually look like this periodic function. In the spatial domain your kernel is this, in the Fourier domain the kernel looks like this, okay, sampled kernel. And this is, so if this is hm, this is hx minus m, which is what you actually require for doing convolution, okay. And now look what happens after you do convolution. The expected result in the spatial domain is this, okay, because somehow there is no space, okay, the space falls short. You need more space on both sides to be able to generate this entire function, okay. So this extra space is provided uh, if you pad the original function on both sides and pad the original kernel on both sides, okay. So that is the basic idea of this wraparound error and padding. And it turns out that the correct padding to apply is of the following length. So choose P to be greater equal A plus B minus 1, where A equals number of samples of F, B equals number of samples of H. Okay, this is in one dimension. In two dimension, the same thing can be carried over. Pad and padding a M cross N image with P equal to twice M and Q equal to twice N zeros takes care of the wraparound error. Okay, suffices. So I'm stressing this point or writing about this because this will come about as one of the steps for filtering. Okay. So the final thing that I want to talk about is the summary of steps for filtering in the frequency domain. And this I will maybe include in the notes later, but right now I will just refer to it from the text. Okay. Page 266. What are the steps in filtering when you do it in the frequency domain? Okay, so now you should be familiar with all these words that are coming here. Okay. The reason why I went through the trouble of talking about all these properties. Yeah, so the first step is you are given an input image of size m by n. You obtain the padding sizes p and q as described before. Okay, p equal to twice m, q equals twice n. So you pad the image. Then, so you form a padded image of size p cross q using whichever method. Okay, whichever method is required or is suitable. Then you remember you have to multiply this padded image by minus 1x to the x plus y to center the Fourier transform. Okay. So first that is done, then apply the discrete Fourier transform. Okay. So this is just changing the image. Now you have to look at the kernel. Okay. So construct a real symmetric filter transfer function HUV. So this plays the role of the kernel for convolution. Okay. Of the same size. centered at p by 2, q by 2, which will be the center of this also. Okay. Then you form this product. You want to form the product in the frequency domain to get the convolution in the spatial domain. So you form this product. Okay. Obtain the filtered image by computing. So now you go back, right? So you have to compute the inverse discrete Fourier transform of GUV by whatever method. So there are these standard algorithms for this. And now you will have some extra because you padded the image and did all this. Okay, so there will be some extra size there. So you obtain the final result by extracting the required M cross N region from the top left quadrant of the result you get here. So these are the steps of filtering in the frequency domain. Okay, so I mean, you don't need, for example, at least in MATLAB, I know that when you're doing this, okay, there is a function for padding, which you call. There is a function for calculating this. Then there's a function for multiplying. There is a function for calculating DFT. So each of these, there's a function for doing it in MATLAB. Okay, I'm sure that similar functions are available in Python also. This process where you, step number 5, construct a real symmetric filter. So this you can construct by hand. You can actually construct a filter, or you can use some of the inbuilt filters. Okay. So both things are possible. So I will talk a little bit more about this in the final lecture that I said about all kinds of filters. Okay. And then of course you can compute IDFT again by a standard algorithm, okay, and get the final result by cropping. Okay. All right. So